we used to run something called as game day. Now, this is basically a simulation of how an actual match is going to be. We used to generate not just traffic, we are simulating the entire operating protocol. We'll say that, okay, the match is going to start at 7 p.m., let's say. Okay. Now, every system is supposed to scale beforehand. There's a timeline to it, there is a checklist to it, and so on. No matter whether the teams are ready or not, we will start the live stream and we'll start sending traffic.
Wow, really? You did that?
They don't know what the traffic is going to come, what kind of a pattern is going to come and anything, because that's the exact setup of production. You don't know what is coming your way.
Ashutosh Agrawal was a software architect and principal engineer at the largest streaming service in India, JioCinema, now known as Disney Plus Hotstar. In the middle of 2023, the system he architected set a world record at the time with 32 million parallel connected live streams during the finale of the Indian Premier League cricket tournament. But how did they do it? In today's episode, we cover how live streaming works behind the scenes and how large-scale live streaming systems are architected, the trade-offs in system design, and how server-side load, stream latency, and stream smoothness are all connected, the importance of capacity planning and drills, including what the game day drill meant at JioCinema, and many more details. If you're interested about large-scale systems or live streaming, this episode is for you. If you enjoy the show, please subscribe to the podcast on any podcast platform and on YouTube. Welcome to the podcast.
Thank you. Thank you, Greg.
Can you help us imagine what it was like going back to the day this world record was set? It was 32 million, roughly that many concurrent connections at the time. What was it like, like on the day you knew this big match was coming up? There was a system that you did architect, preparing it for scale. But then, you're getting a larger than ever spike. What happened? Were you in the office? Was it at home? Was it stressful? Was it chill?
Sure. So most of the world records which you have set in the past is generally set on the finale of the event, right? And by finale, you're probably settled into the event. These events are not like one-off or one-day event like how it happens on other platforms. Indian Premier League is like a 70-day event. So it's a 70-day continuous madness, right? And every day is more than 15 to 20 million users watching, and depending on the game, depending on the players who are coming in. So it's not like that. To be very honest, the finale is relatively more calmer than the opening week. The opening week is where the most of the madness is there. By finale, you understand the traffic pattern better. You understand what your requirements are. Your protocols are much more set in depth. So in the initial part of the game, it is all chill till you're operating under the numbers which you've planned for. The moment you start to see it getting into the yellow zone, is when things become interesting, because then you have to kind of get away from the auto mode of like a car driving or running the platform to a manual mode, which requires you to be looking at all the metrics, looking at every issue which is coming in, ensuring that you're triaging it on a very short period of time. Otherwise, what will happen is that they will become noise. So you have to also ensure that the ongoing issues is a clean board. And in terms of setup, we typically prefer to be in the office into the same location, because if there is an incident, it is much easier to get into a room with all the key people and be able to take calls and make decisions. We have done this setup in remotely as well. We had a strict protocol on how we operate remotely to ensure that there's not much of madness. It's very easy for the Zoom call to go crazy. Like a Zoom call, the Zoom call on which all of us are connected is over 200 people with multiple partners across the globe present over there to support the event, right? It's just not our team or my team. It's like multiple partners of partners who are present on the call, who are helping us scale through the event.
This episode is brought to you by WorkOS. If you're building a SaaS app, at some point your customers will start asking for enterprise features like SAML authentication, SCIM provisioning, and fine-grained authorization. That's where WorkOS comes in, making it fast and painless to add enterprise features to your app. Their APIs are easy to understand, and you can ship quickly and get back to building other features. WorkOS also provides a free user management solution called AuthKit for up to 1 million monthly active users. It's a drop-in replacement for Auth0 and comes standard with useful features like domain verification, role-based access control, bot protection, and MFA. It's powered by Radix components, which means zero compromises in design. You get limitless customizations as well as modular templates designed for quick integrations. Today, hundreds of fast-growing startups are powered by WorkOS, including ones you probably know, like Cursor, Vercel, and Perplexity. Check it out at workos.com to learn more. That is workos.com. This episode is brought to you by CodeRabbit, the AI code review platform transforming how engineering teams ship faster without sacrificing code quality. Code reviews are critical, but time-consuming. CodeRabbit acts as your AI copilot, providing instant code review comments and potential impacts of every pull request. Beyond just flagging issues, CodeRabbit provides one-click fix solutions and lets you define custom code quality rules using AST graph patterns, catching subtle issues that traditional static analysis tools might miss. CodeRabbit has so far reviewed more than 5 million pull requests, is installed in 1 million repositories, and is used by 50,000 open source projects. Try CodeRabbit free for 1 month at coderabbit.ai using the code pragmatic. That is coderabbit.ai and use the code pragmatic. Let's go into the specific details. We're talking about live streaming. Can you explain us how does video streaming work behind the scenes at an architectural level?
Sure. So let me share my screen to talk about how it works. Just give me a sec. So there's something called a source feed. Okay. This source feed is coming from venue. So from venue actually source feed comes afterwards. From venues we have feeds like camera.
So like the venue is in this case like the stadium where the match is played, right?
Yes.
And then you've got a bunch of cameras there.
Yes. So all the cameras are actually connected over fiber. All of that come to PCR. PCR is a production control room where like all the feeds from stadiums are coming, and then there is a director. So it's like a movie production where there is a director, there's a producer, there are people who are operating the cameras. The director is telling to the person on the ground that which camera to use, what angle to show, and which feed, and so on. So all of that is happening over there.
Lots of people, lots of yelling, lots of screens. Like in the
that's
movies.
a place where we are not allowed to go in if it's on air. it's like nobody is allowed to go in over there, to be very honest. From PCR we get something called a source feed. This is basically what the actual production feed is. Now this source feed is something which comes to. So I'm talking about the video part of it. Then I'll come to the server side or the backend part of it. This source feed is then fed into the there is something called as contribution encoder. Okay, this contribution encoder's role is to convert the source feed into more, because the source feed is a very high quality. You need to compress it a little bit so that you can stream it to the cloud. And then from there, the source feed goes into the cloud, which is like a cloud ecosystem, like an AWS or a GCP or wherever the encoding is happening. This is kind of again a peer-to-peer private link. So it's nothing over internet, by the way.
So this is like your master video feed, high quality, but already a little bit encoded or compressed to manage it.
Yeah, source feeds can be in like hundreds of Mbps or 150 Mbps, right? The contribution encoder will bring it to a standard profile of like 40 Mbps, depending on whether the event is being streamed in 4K, 180p or something like that. From there, it goes into cloud. And within cloud, there is your distribution encoder. Okay. And this is the system which is taking care of encoding it for HLS, Dash, or whatever formats the user is going to consume into. And this distribution...
So with the HLS and other formats, these are like the formats that different players will be able to support, right?
Yes. So the output is like an HLS stream or a Dash stream. Different combinations of it. Like you have a different type of stream for mobile, you have a different type of stream for TV. Because again, the form factors are very different. The network on which they are going to operate is very different. So all those combinations, we output like in past we have outputted more than 100 variants of streams to the CDN.
Just so I understand, so you are transforming it into multiple, like you create all of these different ones, right? Like as you said, up to 100 of them.
Yeah. So actually, if you think about it, there are multiple source feed by different languages. Okay. So we used to stream in like about 13 plus languages. So there will be one source feed coming for each of the languages, and with platform combinations and all of those, the output feed gets into a range of like 500 plus kind of a number. So it becomes huge.
This whole thing is becoming a lot more complex than you would have thought.
Yeah. So and then there is an orchestrator on top of it. This is where our engineering comes in, right? This is mostly whatever I'm talking about is probably using some partner technology and stuff like that. Then there is an orchestrator, which is basically controlling all of these systems, not at the piece, actually not at the venue and source sheet. It starts from somewhere from contribution encoding to your cloud infra orchestration, what endpoint to push to, what should be the config of distribution encoder, and what CDN endpoints to use to. All of this is managed by the orchestrator. So this is our engineering product, which is orchestrating, because on a single day, we are not just hosting IPL. Like we used to not just host IPL, we used to host other events as well. There are a lot of football games going on. There's a lot of other esports events which are going on and so on. So while our focus is on the Indian Premier League, but we also have we used to have other 50 events to take care of. So this orchestrator's role is to ensure that all of that workflows are set up properly. And from here, what happens is this orchestrator sort of generates a playback URL. So we now, the orchestrator takes care of knowing what the final playback URLs is going to be, which is your playback endpoints. Okay. And then once the feed and everything is started, it will send it something called as a content management system. This is what our users are interacting with. So orchestrator will push all the generated playback URLs over here.
And the playback URL. So is this like the endpoint of a node or a machine that has the right format? Like
No. It's not an endpoint of a machine. It's an endpoint of the CDN where the video would be available. So for every TV, mobile combination of Apple, Android, and whatever variants exist, for each of them, we generate a playback URL. So playback URL is a certain spec, right? And along with that spec, we push it to the content management system. This is your client apps are generally interacting with your content management system for rendering the browsing experience, right? Whenever you open the app, you're seeing the content list of contents and everything. So this is how it does, but that's not all, right? This is just for a browsing experience. And typically to scale, you would put a layer of good enough caching in between to ensure that things are scalable in nature, right? Like that's one of the secret sauce of making things work. Now, this is about browsing experience. So far, what we have spoken about is that you can open the app, you can see the content, you can click on the content, you can see the details of this thing. The moment you hit a play button, you call a much more complex system, which is generally a playback system. I cannot talk about exact internals of it, but this system is responsible for ensuring that the user is authorized to watch the video. It will talk to a user system. It will talk to encryption and DRM systems. It will talk to the content management system, and then give you a kind of an encrypted URL, which is what the client will use to play back.
And are we talking about live streaming, or is this playing back existing streams?
This is for live streaming. The only difference in whatever I'm showing in the diagram is all about live streaming. In a VOD system, you would not have this complex setup like over here, how you have the contribution encoder, cloud, and distribution. It'll be a little bit simpler. There will be a single encoder which will encode and put it into the CDN. And there would be a similar orchestrator for VOD content, which will take care of this. So the workflows are almost similar, but there are more complexities on this part on how to select which URL to play back in live streaming than on a VOD system.
Mm-hmm.
Yeah.
One question I have is, you mentioned CDNs, but CDNs are great for caching stuff and making sure, spreading it out so that they're on the edge. But this is a live stream, right? Like every I don't know 100 milliseconds, you will have new frames arrive, or every I'm not sure how that's done. But how does this square with the fact that like CDNs are great for caching, but they might not be the best for real time stuff, or are they good for real time?
So they are actually. See the secret sauce of how live streaming works is in the HLS and the dash spec, to be very honest. I can talk a little bit more about HLS so that you get a sense of how it works, right? See, HLS, you have something called as a master manifest. Okay. So whenever you'll see a playback, it will look something like master.m3u8. Okay. In this master manifest, you have multiple informations. So it will contain information of saying that this is a 240p video, and this is it will point to a child underscore 240p.m3u8 and so on. Then similarly there would be this 480p and so on, right? So you would have layers of manifest, right? And this is so what happens is within each of the child manifests you would have a list of segments. Okay, segment1.ts. It is we can use TS.
Is a segment a certain time period within a?
Yes. So I'll just
how long are segments usually?
Yeah. So that is configurable. That is all subject to how we design, how we look at what kind of a latency do we want to offer to the users on the accessing. So typically they are between 4 to 6 seconds is what widely used in the industry. So what happens is
4 to 6 second files, right?
Yes.
One after the other.
Yes.
Okay.
Yes. So what the client is doing is essentially in HLS protocol is it when you initialize the video, it calls a master manifest. Then it gets the list of all these child manifests, and it is keeping track. So based on the start bitrate, based on the network condition the user is, it will pick saying that, okay, this user should start from 480p or 720p or so on. Okay. And then the child is just calling this manifest again and again. And if your segment duration is, let's say 4 seconds, it will call the child manifest every 4 seconds and asking for an update. Okay.
And asking for the update will be the next file, the next part of the next segment.
So this is like a windowed manifest which has like 200 plus segments. Typically, you select a duration which you want to keep in the manifest, and the player is kind of polling this manifest and getting the list of segments. So as soon as it sees a new segment, it will go to the CDN, request and get it downloaded and put it on the buffer of its own. So that is how it works. So the role of the CDN is that the CDN is not operating at 100 ms is what I wanted to call out. The CDN is operating at a 4 to 6 second gap. But still, with so much of caching, it becomes tricky. And this is where our engineering works, is how we tune and fine tune the CDN configurations. What is the right TTL to use and so on, right? Because if you use too short a TTL, then everything is expiring and you're always missing a cache.
Yeah.
And if you use a very long TTL, then you have a chances of hitting in stale data.
Yeah. So it's a fine game. But now I guess I now understand, when there's a big game happening, may that be the World Cup or something like that, and you're watching it on the stream, every now and then you hear a massive scream from the neighborhood. And then 2 or 3 seconds later, you see the goal or see the team scoring. So I guess this explains, right? Because there will naturally be roughly up to a few seconds of delay, depending on which endpoint you're hitting, depending on when you started the stream. Yeah,
good that you brought in this in, right? Like I'll explain. So every time, any encoding system would be more efficient if it has a look back period, right? So if an encoder wants to be more efficient, compression technology is like saying that, hey, I have a reference frame and these next frames are delta from this reference frame. So for compression to be more efficient, if you can look back more and more, you will be better, right? So there's something else called as group of pictures or group of GOP, right? You say that my GOP is 2 seconds or my GOP is 1 second or 4 seconds, which is to say that, okay, I'm going to look at optimized compression for this. So every encoding stage will add to that latency, which you're talking about. So that is one place where your latency is added. Then the other latency is added on the client side. Now, when you're streaming on a internet versus a TV, in TV, what will happen is that if you miss downloading a segment, like in segment equivalent or of certain frames, you'll probably see a blackout and you'll move forward. TV is not going to let you be, it will not going to optimize for you to be at the right place, right? It is always the latest point you're seeing because it's a broadcast protocol.
It's real time.
It's real time, right? So if you miss something, you miss something. Like if there is a rain and you miss to get that packet on the TV, you'll miss it. But in internet streaming, every user is maintaining a buffer, right? And to ensure that you get a smooth streaming, you will always have some buffer configuration on the client side, which will be taking care of like your smoothness, right? So what happens is whenever you start a playback, you're always starting a playback from 5 seconds to 10 seconds behind the live point. Because if I keep you on the live point and there is problem for any reasons, right? It's a distributed computing, it's a complex system. For any reason, if you miss out to download that particular segment, you will end up seeing a rotor and you will have a bad experience. So it's a fine choice when you're doing it about scaling versus number of devices you want to support versus continuous, like a better UX versus a more live point, right? I like we found a sweet spot somewhere where it works for the users. Again, I cannot disclose the numbers, but that's the complexity behind it.
Yeah, but I really like, because in the sense of like, okay, well, this is the reality, but this is what it's about, right? Trade-offs. Like
Yes.
you can choose between having, like some latency, okay, 5 to 10 seconds, but then it works pretty smooth for most users, and you don't have crazy infrastructure requirements. Or if our requirement was, like I don't know, someone came up with like you shouldn't have more than 500 milliseconds. You would need to architect a lot bigger system, a lot, different trade-offs, right?
So I'll give you an example, right? Let's say you have 4-second segments, okay, and you're polling for you're downloading 15 segments in every minute. You're downloading 50 manifest calls. You're making 30 calls to the CDN every minute. Now, if I change the segment duration to 2 seconds, your volume of calls will double, which means even though you're downloading the same amount of data, the number of requests which will be hitting, which the amount of compute cycles which will trigger on the CDNs will increase, right? And no matter whether we say the internet and cloud is infinite, it is not really infinite. There is finite amount of space and resources and everything. So when we are designing for scale, you have to factor all of this in. We have to factor all of this in from the perspective of capacity, from CDN capacity. So sure, your networks have gone to 5G and all of that, right? But there are so many choke points within the infrastructure that you have to account for, you have to be aware of. So, and that is where the playback system becomes very crucial, because it is aware of all these nuances and deciding the best experience for the user.
Yeah, and I guess it just shows how different internet streaming is versus traditional television. Like when you had an analog signal from the radio go out, it's just you send it one way, every device catches it. And
if it catches it, it catches it. If it misses it, misses it.
As you said, or when you have more traditional cable, the cable connection to the TV, again, you just push out the signal. It's the same real-time signal. So it just doesn't have this level of, you don't need to worry about the internet infrastructure, the internet providers, your bandwidth, all of this changing. It's fascinating. I do have one question related to this. Adaptive bitrate streaming is a word that I've heard, and I can kind of imagine what it means, and you kind of already touched on it. How does it work, and who controls the adaptive bitrate? Is it the server? Is it the client?
So it's mix of it. Largely the capability is driven in the player, but it's all about fine tuning. Like adaptive bitrating is if I were to simply explain it, you have a network speed of 4 Mbps. Every layer which you see within the video, which is 240p, 480p, every layer has an average bandwidth. So 240p would be probably at a 200 kbps, 720p would be at about an Mbps, and so on. So what your player is doing is, as and when it is downloading the segment, it is also measuring your bandwidth. Because you're downloading a 4 MB of, let's say, a segment chunk, how much time it took. So it knows an average speed, right? And when it sees that it is drifting apart, like your download speeds are getting slow, it will recalibrate, and the player would jump to a lower layer or this thing.
So
right?
it goes to the manifest and says like, hey, could I have the 240p, because I can measure that I'm not fast enough to download all this.
Yes, exactly. So that's where you see the blurring of the video, and all of that seamless switch is taking care of the player. But that is the simplest implementation of the ex-Jio player or the client-side player. Now, if you do that and you try to run an IPL match on that, I don't think it will work. You'll encounter numerous issues. You'll get a bunch of customer complaints and so on. So there are a bunch of parameters which player allows you to control. Like what threshold to choose to switch between layers. What should be your starting bitrate? What should be your threshold for error? What is a buffer? What is a buffer duration which is left before you make a decision to switch? So all of that, those parameters is something which is fine-tuned when we are doing engineering, right? And some of these parameters are governed from the server as well. So the server is also looking at how things are operating around the world, like in the entire ecosystem, and making some calls. So if you have to do degradations, the server can choose to do degradations by limiting the number of layers you're accessing it.
So what you're saying is when my server is getting overloaded, you also have the choice to start serving either like longer segments, lower bitrate, etc. in order to you're going to make these decisions.
Yeah. So again, the the place where I was saying that I'm pushing to CDN numerous combinations. There are some combinations which are designed from a reliability perspective that, hey, we can offer the best experience up to a certain concurrency, but after a certain concurrency, we might have to switch users to a little bit more degraded. So
it makes sense, right?
Yeah. So all of this is now part of the engineering which we used to do. This is not something which CDN offers, right? And so CDN is sure handling much more lot of segment delivery and stuff, but that orchestration is where the tricky business is.
Yeah, so I guess is it safe to say, just, there's that thing where you're streaming something, may that be a live video, either a live video or video on demand, and when it gets blurry, I guess two things can happen. Either it's your client side deciding your bandwidth is not long enough, or if it's a live event, it might be that the engineering team or the system decided that in order to sustain all this high load, it needed to switch back to conserve the server resources.
Yeah. So there's third aspect to it, right? Your client, now this is where your equilibrium kind of concepts come into the internet, right? When the congestion starts, let's say you're connected to a tower. Now, 100 people were watching earlier. The tower has a finite capacity to stream downstream to, let's say...
So by tower, you mean like a mobile tower?
Mobile tower.
Like
mobile
a 4G,
tower
5G tower.
4G or a 5G tower, right? They have finite capacity on the number of clients they can handle, like an access point. If they start to get congested, they will start to naturally throttle you or start bandwidth sharing, which will also trigger slow download. So this is not a parameter where I am going and controlling and saying that, hey, the user should get blurry or this thing like that. It is natural, which will happen, right? Depending on the infrastructure layout and where you are connected to.
There's so many layers into, what we started off as just, just stream live video.
Oh, it's funny, right? When we get user complaints, you have to look at so many places. Like, was it our system? Was it our client? Or was it like some intermediary network? And if it's intermediary network, how do you prove that there was a network congestion? Because we do not control those systems. We do not have visibility on the metrics of those systems. So we have to build intelligence on the client to figure out all of this.
Yeah, it's very complex. When I used to work at Skype, and it was on my LinkedIn, people knew, and sometimes people would either message me or a friend of a friend saying, "Oh, you work at Skype." So I had this problem where I had this video call and it got really blurry. Like, why was that? And I was like, like you said, I didn't have as deep of understanding of everything that happened. But you mentioned that you cannot monitor everything. What is it that you can monitor? Because I imagine, just as an engineer, you need to have as much information as possible to, figure out what is the best experience. But there's going to be practical limits and also just kind of data collection limits. So what is it possible to monitor and what is practical to monitor on the client side and then on the server side?
So the amount of data collection and processing you can do is infinite, right? There's no end to data collection and analytics, right? What it comes down to is what will help you to, in a case of an issue or an incident, what will help you to figure it out, right? And the way I describe metrics is that there are leading indicators and there are trailing indicators. Okay, leading indicators are things which will ahead of time tell you that there is a problem about to happen. So we would have 3 or 5 metrics which are defined as leading indicators, and we are very sensitive. We would be very sensitive towards those metrics. Like on the client side, it would be the amount of buffer time you're seeing, which is how many seconds did you see a buffer in a minute, or what is a playback failure rate, which is basically when you start a video, did you encounter a failure, or while watching a video, did you encounter a failure, which is a fatal in nature, like not the app crash, but the video crash kind of a thing. So there are some of these metrics which will be treated as a leading indicator, and these metrics would be collected on the client side. There will be corresponding metrics on the server side. We obviously will be monitoring bandwidth, number of requests coming in, latency, response times, bunch of other things which will be monitoring on the server side. The leading indicators get priority over the traffic. Like you would always want to have them process ASAP within a minute, sometimes under 30 seconds also, so that you are reactive, you're getting alerts before anyone complains to you. So that's where you optimize for. Then you have trailing data, which is basically let's say you figured it out that there is an issue. Now you need to get into the details of it, right? Which and the funny thing with the live streaming is that your time is also moving, right? It's like it's just not that okay, there is a system state or there is a state, right? That the state is also constantly evolving.
Yeah.
So you need to measure a lot, you need to collect a lot of data, and you need a lot of tooling to be able to visualize what is happening and how it is being rendered. So there's a lot of data collection which get processed a little slowly. It's available on dashboards for us to consume and figure it out. But that's how we look at metrics.
And then on the client side, obviously you're collecting all of this data, but then you need to like push it back to the server, right?
Yes,
like every, you know, again, I'm assuming this is an engineering trade-off, like if it's every second, every 10 seconds, every minute, that kind of stuff.
I don't think every second would scale for us. Imagine like 30 million users watching concurrently, and every second they're sending data is like I cannot scale that system, to be very honest.
Yeah, but it's interesting because now, you know, like we have servers, clients downloading, and then we also have the upload of the metrics, which is also this fine balance, I assume. When you decide, okay, even just this relatively simple example of how often should a client upload their leading indicators, how did you decide on, you know, what that will be? May that be every minute or so? Did you know, go to a whiteboard and figure out like, what does this mean for a server? How much can we process? How many petabytes? Was it a mix of prototyping and doing load tests, or was it a combination?
It's combination, right? It's not an easy decision. In fact, during the event itself, the frequency keeps changing. As and when you're scaling, you would be okay to compromise on certain aspects to scale the system and have some sense, right? You will also use some form of sampling as well. You'll use a balanced approach to figure out how to do so. And you can collect all the data at every second level, but you have to process. There is cost associated with it as well, right? So and just not cost. There is, again, cloud is finite. So even though CDNs are finite, even your the cloud service providers also have finite capacity. So you have to take into account that, do you want to prioritize your playback systems and content management systems, or do you want to prioritize data collection? So all of this has a priority and an association to say what tier of the system falls into, and that tier defines how the system degrades. So there's always a degradation framework, which is to say that, okay, if the match is not huge, then yes, we'll collect more optimistically at every 15 seconds or every 30 seconds or whatever that number is. But as the game starts to become hot, or more and more traffic starts to come in, then you would at runtime start to degrade systems, which means that degradation happens in different shapes and formats. You will probably reduce data which is coming in. You will change the interval at which you're collecting data. You would start sampling. All of those parameters start to come into the play. And all of this is part of the design, right? This is all the exercise we do before the game on resource planning, on capacity planning. Like capacity planning is a huge exercise. And that also decides what are the cutoff points, right? Sometimes you will say that, okay, I need to support up to, let's say, X million users or 50 million users or 100 million users. That means you have to work backward from there and say that if I have to support 50 million users, what are the P0 service requirements? And then you say that, okay, this is the residual capacity. So the P2 services have to operate in this residual capacity, which means that I can do certain things, I can't do certain things.
So on capacity planning, you already kind of outlined how it works, but you said it's a big exercise. What does a good capacity planning look like? And you know, like, and why does it take so long? Because, you know, what you describe here, honestly, you know, just do the maths, do this, that, but obviously it's more complex, right?
So capacity planning is a very complex exercise. In fact, for most of the video streaming, the capacity planning for the next year starts at the end of the previous year.
Oh, wow.
Because you have to lay down infrastructure, you have to work with providers to ensure that their data centers have to scale up, their network have to scale up, their power requirements have to scale up. All of that has to be taken care of. It's not that simple. So there's physical infrastructure being involved, right? Like we cannot just providers will not go and scale their infrastructure. Sure, they have a 10% plan, 20% plan, but if you're operating at a much more intensity and adding more year on year, then you have to work backwards from there. So that is one aspect of it. The other aspect is during the tournament, there can be overlap with other events. So there might be reservations done by other companies. Like there's a big e-commerce sale going on. Let's say if there's a Black Friday, like Black Friday is not there, but it's equivalent of that. So the point is you have to look at the resource, you have to figure it out, you have to ensure that you've blocked enough resources for the time period. And the other complex piece is how much to ask. Every year, the nature of the game changes. There is no set pattern. How many people will come in? So there are certain models. We will look at it and see that, okay, this is the user traffic which has been coming in, which was in the previous year. And we have seen platform to grow by X percentage. So we'll apply some modeling to it and figure it out what should be the next year's optimistic number. Actually, not an optimistic number. It's a very pessimistic number. We operate with a very pessimistic number and then work backwards from there. So the reason it's complex is because you have to work with so many providers, understand how much resourcing and all of that is there, which means they have to go back within their engineering teams, get that numbers, share that number of results, and then we do all that.
Just to make it really concrete, are we talking about how many virtual machines you'll need, how much bandwidth you'll need, how much, like, what are the things, the things behind the resources that, you're going to have a list of, like, oh, we need this much?
Primarily, it boils down to the same core system metrics like compute, RAM, disk, and network.
Yeah.
All of that boils down to that. Like every tier has those numbers which you have to figure it out. When you're running servers, it's going to be number of vCPUs. Generally, that is a limiting factor. Disk and RAMs are not limiting in cloud. Network becomes an interesting problem for streaming part of it, not the Actually, it becomes interesting on the API side also, because yes, video you're doing like tens of TBps and probably more than that, but API is also consuming a significant amount of data download. So and those networks are designed differently than the video networks, because video networks are more designed from a heavy caching perspective, that the offload should be super high, but APIs is mixed traffic. There's security, there is different tiers of security, there is PII data flowing in, there is your firewalls and so on. So you have to look at all of those parameters. When I say parameters, again, it's network consumption, compute resources available at each hop, figure out what is the least common denominator and work from there.
Yeah. And then you did mention before that the cloud is finite. Now, I didn't hear too many people saying this, because usually when like I'm a startup, I'm building something that, like, I will be aware of the cloud is expensive, but I'm never going to think that it's finite, because as far as I'm concerned, I can always pay more to, scale up. In your case, that's not really the case, right? So, and this is because you're so large, right? This application is so large.
Yeah. The use case is so large that like year on year, the growth is so much that it's very hard to preempt, right? And as I said, that you're doing pessimistic planning because you want to support best of best. The infrastructure exercise, the growth of infrastructure is relatively hard, because I'll give you an example, right? So let's say in a city like Bangalore or Mumbai, there is a finite number of TVPS available, and the seating capacity available. Now, if you have to add more capacity, the providers need to purchase real estate. They need to add links to it. They need to deploy servers to it. The servers need to be procured, imported from another country. They need to be configured, onboarded as part of the network, and so on. So it's a slow process. It's not. It can't happen overnight.
Yeah. So basically, what you're saying is, let's say you as a Jio or any other streaming service is like, okay, we think that this game that's going to be in 6 months. Last year in Bangalore, 5 million people watched. I'm just saying a number. This year, we think it'll be 8 million because of our projections. We think the current CDN capacity, based on our calculation, is not sufficient. So now you're going to go to the CDN providers and try to make a case for them to invest. That's pretty hardcore. Not even engineering. This is like, it goes beyond engineering.
Yeah, and you started the discussion saying that, hey, why don't you code? Because I feel this is a much more harder problem than actually coding it, to be very honest.
Okay, I'm starting to understand. It's important to stay connected, but it seems like this seems just as important. It's probably more important to do this thing and go to the vendor, sit in a meeting with them and explain to them why you need to order those servers from wherever.
Yeah. And another common question I'm asked on this subject is that, hey, oh sure, Bangalore doesn't have capacity. Why don't you go and get it from Delhi? It's not that easy. Anytime, like if you understand, it's a caching infrastructure. It's a tree, right? So
Well, it's also edge, right?
Yeah,
It needs to be
it's also
close.
edge. Yeah, so it needs to be close. The moment the more upstream you go into a branch and try to get it, the capacity available over there is finite. So if I were to say that, hey, let's route this excess of 2 million traffic, let's say that's consuming about 2 Tbps, there has to be that amount of backbone infrastructure present in the country to be able to route it to another city.
This episode is brought to you by Augment Code. Wish your AI copilot actually knew your code base? Augment Code is different. Augment is built for professional engineering teams working on complex systems, not hobbyists building to-do apps. Other AI assistants struggle with context. Augment understands your entire code base, architecture, patterns, dependencies, and all. We're talking instant understanding of systems with millions of lines of code in under 200 milliseconds. Teams like Webflow, Lemonade, and Kong use Augment to ship better code faster. No more context switching, no more generic suggestions, just an AI that works the way expert developers do, fast and in flow. Plus, with enterprise-grade security and zero training on customer code, you can trust Augment with your systems. Start building with Augment in your favorite IDE and see what it's like when an AI actually understands your code. Try it free at augmentcode.com/pragmatic. So we already touched on this. This is, I think, one pretty good example of like an India/APAC specific engineering challenge. What other engineering challenges have you seen that are pretty specific to APAC? You know, like when you're building a system in Europe or US, maybe you don't even need to think about it. But in your case, you know, it gave you a lot of headache.
So capacity is one aspect of it. The other comes is the mobility. India is a country which is mobile intensive. People don't watch it on TVs or laptops or this thing, right? India is a country which kind of had a leapfrog in terms of generation, right? People who are not using any computers or any mobile devices started onboarding to mobile devices directly. They did not see laptops or tablets or connected TVs and so on. Connected TV is still picking up, but it's still not there at the level at which it might be there in the Western countries. With mobility comes the problem of that, one, the device is constantly moving. It is changing radios and networks.
And you're changing cell towers and all that.
Cell towers and all. A lot of audience are like the taxi drivers or the cab drivers or people who are on the move, who are getting off the office. The event happens in the evening. People are getting off the work.
Yeah, everyone's holding their phone and watching it.
Exactly, right. Like most of the ads used to run like that. So people are watching on the move. So that becomes tricky. Sometimes you're connected to a 5G tower and then you go to a 4G tower and 3G tower and so on, right? Like you're on a train and you're moving at a speed, your towers are switching. That is one aspect. The other is a battery. Most of the games happen in the evening, right? And if you started your day in the morning, you probably charge your phone, you're off the work, you're not getting it out, so your battery. So that becomes an interesting problem to also tackle, right? Like how do you ensure that you're not doing so much of computation on the device that you end up burning up the phone battery.
Wow. This would have not been on my top list of things to worry about, but I guess there you go. You need to worry about it.
You need to worry about it. Like your streaming or your downloads or video consumption cannot eat up the phone battery. Otherwise the user will not watch. So,
and what do you do around this? Like what kind of considerations do you have?
So it's a lot of how much background processing you're running, what's the phone brightness you're using, what's the volume levels you're using, what is the color intensity, all of these parameters, kind of the profile of the video kind of controls how much battery consumption is going to happen, how frequently are you polling, how frequently you're downloading, what kind of complex encoding algorithm you're using. So we're using H.264 versus H.265, the codecs, right? Like HEVC versus AVC, each of the codecs have its own complexity. If you use a more compression, then it means it will use more compute, which means it will consume more battery. So
do you have this thing where it's theoretically possible then to have on the client side, based on the battery level, request a different type of stream? You could do that technically,
we could do that. But the point I'm trying to make is that all of these parameters are taken into account when these are not probably decisions that you make at runtime, because at runtime you would be more focused on, like, you would want to have as less variables as possible. So these would be considerations that you'll probably do when you're releasing features or when you're adding more.
When you're building it.
Yes, when you're building it, because runtime, like I would want to have only one or two parameters which I'm tweaking at runtime. more the number of settings, it requires more coordination, verifications, testing, and all of that, right? Sure, you can have automation, but trust me, automation doesn't work after a point. Like, you need to still have some level of manual testing involved.
Okay, so an event is on, and it's you knew it would be a big event, and more and more people are joining in, and the load just keeps going up, and eventually you set a world record. But as this happens, how can you scale things up? How can you both plan to scale up a system, and what can you do on the spot? And I'm assuming horizontal scaling, I'm sure, will be a thing. But for example, is vertical scaling, basically having bigger boxes, bigger devices, also an option or a practical thing to do?
So I think the vertical scaling, I'm trying to think how much of vertical scaling only happens on the database or the database layer, to be very honest, right? Compute is largely horizontal in nature. We try to, like, for example, if you're using actually databases have also now become horizontal in nature. You can add more boxes and you'll start to split and scatter data. But you would want to avoid any kind of that, like scaling at the data layer at all when you're operating at load. So most of your databases and caches are preemptively scaled pessimistically to a higher number. Compute is what you're controlling on the fly. In fact, auto scaling doesn't work. So you have to always, auto scaling doesn't work for this kind of a workload.
Okay, can you tell me more? I would have thought, the whole point of auto scaling is that it should work, but obviously under the hood it's a bit complex. Can you like give us a bit of a explainer, or 101?
Sure. So
why does auto scaling not work?
Yeah. See, the auto scaling works by adding a box at a certain rate, right? And default auto scaling, which is provided, most of the providers have a cool off periods and bunch of parameters, which is not entirely flexible. So what happens is that when the game starts or when there is an innings break and the audience come back, that's a sudden surge. Mm-hmm. And in our experience, the auto scaling has never been able to respond to that in a very speedy manner. Mm-hmm. So let's say so I'll give you a classic example, right? Let's say before the innings break, you were operating at a 20 million concurrency. I'm making that number out, right? Now, innings break happened. 15 million people chose to drop off. 5 million stayed back. Now, when the innings recover, you would have 20 million people coming in. But the auto scaling is not going to respond with that number in mind. It will be like, oh, I'm seeing this much of traffic, RPS, let me add more boxes. But you have to understand that there were already 20 million people which are on the stream. So after the innings break, you have to go back, right? So if you use auto scaling, you will be screwed. So that's why we used to have our own custom scaling systems and custom scaling providers. And that will look into a concurrency. Concurrency is a metric which we would align to and say that this is the golden metric to scale against. We will build models to translate that to every system services. It's because it's easier to talk in that language than actually talking in another language. Like every system having a different metric to scale against is complex than saying that everyone in the company is scaling against a common metric. And we are very solid and sure about that this metric. So you can compute and saying that, okay, I have X number of concurrent users, which means that this is the traffic I would expect on XYZ services. This is my user journey. 100 people open the app. Y number of people go onto the playback page. Then Z number of people open this. So there's an entire formula which you can build out. And then you can, from there, map back and say that, okay, this is the amount of request you would see. And there will be certain systems. I'll give you an example. When the innings break happen, again, innings break or some kind of an event happens, let's say a key bowler or a key batsman get out, right? What people do is people have a tendency to press back button. The moment they press back button, they go on to the...
Press back button, you mean the exit stream, or they want to just rewatch it again?
No, they just want to go back, like close the stream and go back to the home page. Right?
Oh, gotcha.
So exit, like either the people will just swipe up and close the app, but a lot of people will press a back button. The back button will take these users to the home page. And homepage has a different set of APIs to be called, which was not seeing the traffic at the rate it was seeing before.
And they're going to have a big spike.
Exactly. So all of that intelligence can't be taken, like answering your question on why auto scaling doesn't work is because of these UXs and user journeys which cause problems. So we have to ensure that...
So basically you're saying that the whole company, or the team will know that this is our concurrent user target, and every system just needs to prepare to potentially in a single second get that many requests if people, like in your example, was hitting the back button and fetching the home page.
Yeah. So we have custom scaling and so all of this is present. So that's how the systems are taken care of. These custom scalers are constantly watching at the concurrency number. Whether the concurrency number coming and being reported is accurate or not is a big question. So you need to have triangulations and proxy to figure it out whether the concurrency number coming from the system A is correct or not. Because if that gets messed up, your entire scaling gets screwed. So
you've given us already a very deep dive into video streaming, and we probably just only scratched some of the surfaces. But how did you learn all of these things outside of on the job? Are there additional resources that you do, or you kind of educated yourself? Basically, if someone wants to understand a lot more about live video streaming, what are recommendations you would give them? And and they don't have the opportunity to work at a company like you did just yet.
Yeah. So I think this is a nice part and the sad part. You cannot Google our issues. There's no Stack Overflow for our issues or the things we experience, to be very honest. Some of the things around the video there's plenty of good resources around the video. There is a GitHub link. I'll probably find it and share it with you. That has a very detailed explanation of how video works. It starts from text and then goes on to how image is done, how image compression is done, and then how image becomes a video. Frame by frame description. There's a very good document around it, and so I can share that. So that is something which I learned. Rest all of the stuff is on the job. Like, I don't think these problems are something which are available on the internet anywhere.
And then on the job, what were things that helped you become a lot more experienced, reliable senior? Like what kind of approaches or mentality helped you to soak it in just really quickly?
So I think for me it has been planning and like the entire exercise of going through and drills. So we used to run something called as a game day. Okay. Now this is basically a simulation of how an actual match is going to be. We used to
so you were like simulating this highest traffic event ahead of time.
And not just traffic. We are simulating the entire operating protocol. So we'll have
wow, really? You did that?
Yes. So we'll say that okay, the match is going to start at 7 p.m. Let's say. Okay. Now every system is supposed to scale beforehand. There's a timeline to it. There is a checklist to it, and so on. No matter whether the teams are ready or not, we will start the live stream and we'll start sending traffic. Okay? Because in a live event scenario, you do not have a green light. You're not carrying a flag to say that, okay, the train or the traffic can come in, right? The game is going to start at 7:30 p.m. It's going to start at 7:30 p.m. No matter whether you like it or not. So we used to do those kind of a drill. And in those drills,
in this drill, just so I understand, were you simulating, like synthetic traffic, or was it more that every team had to scale up, like do whatever
synthetic traffic? We would generate terabytes of data.
Really?
Yes, we would generate.
So there was a team that was spinning up, like pretending to be users.
Yes. So we used to have a framework to simulate that kind of a traffic. There's a platform called flood.io which we used to use, which will actually flood it. And we will not give teams access to that dashboard.
So like they wouldn't know what's hitting them.
They don't know what the traffic is going to come, what kind of a pattern is going to come, and anything, because that's the exact setup of production.
Yeah.
You don't know what is coming your way. You need to have your systems being able to tell you whether they are in a healthy state or in a bad state. So all of this is like learnings from there, and most of the learnings, like I've been into this industry for about like 7+ years, right? And it's not like we reached that 32 million number in a single year. We've done smaller numbers and figures. So over the course of time, also you have learned, and while building the systems, we learn from them.
Well, and one thing that I appreciated that you told us is, I was very focused, and I think everyone's focused on like, when you set the record, but you said something interesting, which was it was a 70-day marathon, and the beginning was actually a lot more challenging, and it wasn't setting records, but it was already the traffic patterns, dealing with all of those things. So I think it's a good reminder that, like sometimes it's not the thing that gets the most publicity that is the hardest work. It's the work that you put in before.
No, the first week. So it's a 70 to 80 days, by the way, not 7 to 8 days.
Whew, wow.
It's like
those of us who
intense.
we're not following cricket, and we're just used to either football or other games where it's just a lot shorter. It's a very long time period.
It's a very long time, and it can get very intense on people as well. Right? Like it's very stressful. Every day there is a match. Some other days there are two matches, like back to back, and two matches a whole complicated scenario. Because how do you switch from one match to another match, traffic shifting and all of that becomes super complex. It's not that straightforward from an operational point of view. So the first week is very intense. The days before the first week is very intense. But after that, you start to settle in. We also try to aim that every year on year, we have improved on our operational protocol, automated a lot more. So I think someone was telling me that, so I moved from Hotstar to JioCinema, right? At Hotstar, the level of automation that reached is like people can actually be on a coffee and the live stream match of up to 20 to 30 million match can just run without people.
Oh, well, over time, it gets easier.
Yeah.
So for engineers who would like to get better at architecting systems, what were things that helped you in between, building them, coding them, being in these meetings? Were there, and I'm talking not really about live streaming. Now, this is more like generic software engineering. Would you have advice on activities they can do, behaviors they can pick up that helps you just learn faster?
So there's certain things which I have followed. I can share what I do, and probably that can, if that helps. So I think one of the things around scaling and building complex systems, which I've learned the hard way, I would say, is that you must understand anything and everything which can fail will fail. Murphy's Law. Okay. It's people are very overconfident about their systems. They're like, hey, we have done everything. We have scaled databases. We have done transactional systems and all of that and so on and so on. They underestimate. Okay. And I can tell you, like I have countless examples of where people have come to and said that, hey, our systems are scaled up. Everything is fine tuned. This is good. And I have broken their systems in load testing.
And you're good at making friends, I can see.
Yeah. So like it's people don't like me and doing those things.
I'm just pulling your leg.
Yeah, but I'm just saying that's one core principle which I feel is super important. The moment you get deeper into that principle, you start looking at everything within your system, every decision, every configuration, everything, because you know that configuration at some point can miss. Even the smallest thing as database connection, pool sizes, the number of connections you're making to database, the number of servers. Like for example, someone said, hey, our connection pool size are fine-tuned, we can scale infinitely. Now, but there's a cap on number of database connections you can make to a database, right? So you need to ensure that. So when you're scaling compute, this compute can scale up to a finite number, because if it goes beyond that, it'll start choking databases. Then your requests and queries will start to get queued up, which will increase waiting times, and so on, right? That is one, right? The other is metrics and measurement. It's very important to have very detailed measurements in place for your systems to be able to figure out where the problems is. Kind of a water flow and this thing. Like there's a common paradigm problem I've seen with every engineer, right? So you know how you measure response times, right? Now people go and measure response time by looking at the on the load balancer that this is my request and this is the response time. Now, even in the load balancer, there's a request. The way the load balancer was, there's a request queue. You request queue, request gets queues, and then there's a like a cron or like a worker which will pick up the request and process it. Now, the way you measure response latency is from the time you queued the request to the time you return the response. That is your response latency. Now, what people will do is people in the processing function, which is listening to the request, will put the timing function to start of the processing function and end of the processing function, which will get response time. But they're like, oh, my server is working all fine. Everything is good. My response latencies
don't notice that it's sitting in the queue.
It's sitting in the queue. And this is the same problem which can happen down the stack. So that is the level of detailness you have to go through when you're designing metrics and measurement.
I guess what I'm hearing is it also really helps for you to just don't, go deep and understand exactly how it works. Because, for a load balancer, like it's kind of easy. It's like, it just balances a little bit. Once you go in there and understand, like, how is it implemented? What kind of queue does it use? How big can it be? All of the internal latency, etc. Yeah. That's good advice. Thank you.
Yeah, so that's one. Third thing is, I hate APMs. I've never used APMs in my life.
Application performance management, yeah.
Yeah. So a lot of people say that, hey, why don't we put APM? We can figure out stuff from there. Now, APMs have at least this is my biased opinion. I feel that it makes you lazy. Sure, it can help you get all the metrics and everything in place, but people become lazy. People don't get into the deeps of their system. They're not measuring. They're relying on APM to do the right things for them. And sure, APMs have evolved over the course of time. You can argue. I'm sure if this video goes out, people have a lot of views on it. But the point is that I feel like it makes you lazy. Not having APM forces you to go into the details, forces you to look into every corner, forces you to measure every aspect of your code, measure every performance of your code, and fine tune it.
Well, thank you. And to close it off, we'll just do some rapid questions.
Sure.
I'll fire a question and then you just go what comes to it.
Yeah.
What programming language are you the most productive with, and which one is your favorite?
So for building systems and services, I use Java. Otherwise, for scripting or a script junkie, I'm very familiar with Ruby, and Ruby is my go-to. Like it's for me, it's
nice.
like English. Like you're writing English and it just works. So Ruby is my go-to for any scripting work and kind of stuff.
Nice. It's a friendly language. I mean, most people will use it because of Rails or together with Rails, but by itself, it's a nice language, no?
Yeah, I started with Rails actually. My career started with Rails, but then I got hang of Ruby. Like it's very easy. Like if you have to process some data, like you have to analyze something, you write some model, you just write in Ruby. Like you get all the gems, start working, you just get it done.
What are some blogs or websites that you read to keep up to date?
So I read a lot of Hacker News. Hacker News has a lot of fun content and latest content over there. Then LinkedIn is a good source, to be very honest. Like somehow the network of people I have is like they keep posting a lot of interesting stuff. So I get a lot of good content from there. Apart from that, I have keen interest on latest technologies. So like CES events or some of the events which are happening. What are the talks being presented? What are the things being spoken about? Is something I keep a tap on.
Awesome. Well, this has been just very, very interesting to go into like all the complexity of something seemingly so simple as live video streaming. Thank you very much for sharing all this and for being on the podcast.
Yeah, thank you. Thank you for inviting me. Like it's been a wonderful conversation, sir.
Thank you to Ashutosh for taking us behind the scenes of building a large-scale live streaming service and one that set a world record at the time. Check out the show notes below for references we mentioned in this podcast and to see related deep dives you can read in The Pragmatic Engineer. If you enjoyed this podcast, please do subscribe on your favorite podcast platform and on YouTube. Thanks, and see you in the next one.